In the first lesson to this section of our STEM instructional program, we introduced you to the four forces that impact the flight of an aircraft. In this lesson, we're going to focus on the concept of lift as it applies to aircraft. These same concepts will also apply to helicopters and lighter-than aircraft, but the mechanisms used to generate lift in these aircraft are significantly different. We are going to discuss how lift is generated in an airplane and how it affected the other three forces: thrust, drag, and weight. Lift is the force that directly opposes the weight of an airplane and holds the airplane in the air. Lift can be generated by a wide variety of objects, including airplane wings, rotating cylinders, spinning balls, and flat plates. Lift is generated by every part of the airplane, but most of the lift on a normal airplane is generated by the wings. Lift is provided differently in helicopters and lighter-than aircraft. Those concepts will be discussed in separate lessons. For an aircraft to leave the ground or stay in the air, the force of lift must be at least as large as the force of weight of the airplane. Because lift is a force, it can be represented as a vector quantity having both magnitude and direction. When we look at a vector representation of lift, we would see that lift acts in a direction that is perpendicular to the motion of an object. Drag, which we will cover in another lesson, acts in a direction opposed to the motion of the object. Lift is produced by the interaction of a solid body with a fluid. It is not generated by a force field in the sense of a gravitational field or an electromagnetic field, where one object can affect another object without being in physical contact. For lift to be generated, the solid body must be in contact with the fluid. In other words, if there is no fluid, there is no lift. Without air, there is no lift generated by the wings of an aircraft. Lift is a mechanical aerodynamic force generated by the motion of a solid object and a fluid, which may be either a liquid or a gas. To generate lift, there must be a difference in speed or velocity between the solid object and the fluid. If there is no relative motion, there is no lift. It makes no difference whether the object moves through the stationary fluid or the fluid moves past a stationary object, or both the solid and fluid are moving at different speeds. There are many explanations for the generation of lift found in encyclopedias, in basic physics textbooks, and on websites. Unfortunately, many of the explanations are misleading and only partially cover how lift is generated. Theories on the generation of lift have become a source of great controversy and a topic for heated arguments. To help you understand lift and its origins, we will review and describe the various theories and how some of the popular theories fail to explain lift in different situations. Students of physics and aerodynamics are taught that airplanes fly as a result of a principle developed in 1738 by Daniel Bernoulli. In simple terms, the concept says that if a fluid, such as air, is forced to accelerate, the spacing between the molecules also increases. If the molecules are farther apart, the pressure exerted by those molecules on the wing of an airplane is also lowered. This seems to explain the generation of lift in a typical aircraft wing that is asymmetrical or not symmetrical. In this type of wing, the distance that the wind must flow over the top of the wing is longer than the distance the wind must flow under the wing. In order to meet up at the trailing edge, the molecules going over the top of the wing must travel faster than the molecules moving under the wing. Because the upper flow is faster, then by Bernoulli's principle, the pressure on the top of the wing is lower than the pressure under the wing. Thus a wing generates lift because the air goes faster over the top, creating a region of lower pressure than under the wing. The difference in pressure across the airfoil produces the lift, with a net upward force. While many lifting airfoils are designed to have the upper surface longer than the bottom, that is not always the case. Think of a paper airplane. Its airfoil is a flat plate whose top and bottom surfaces are exactly the same length and shape. The first aircraft had wings that were shaped more like the bird's wings, with concaved bottom surfaces. Some aircraft have a symmetrical airfoil that generates lift despite the fact that its upper surface is the same length as the lower surface. There are modern low-drag airfoils which produce lift on which the bottom surface is actually longer than the top. Bernoulli's theory also does not explain how airplanes can fly upside down, which happens often at air shows and in air-to-air combat. The longer surface of the wing is then on the bottom. So the Bernoulli concept, while correct, cannot completely explain lift in all situations. This part of the theory probably got started because early airfoils were curved and shaped with little difference between the top and bottom flow speeds. Such airfoils still produce lift and flow turning. If the distance that the air has to move and the speed and pressure differences cannot fully explain lift, maybe it's the turning that's important, not the distance. A second theory of lift supports the concept that lift occurs when a moving flow of gas is turned by a solid object. The molecules of air passing the wing attempt to follow the shape of the wing. To cause the molecules of air to change direction, or speed, a force must be applied to them in the direction of the change in motion. That force is applied by the wing itself. If the molecules are forced in one direction, they also exert a force equal in magnitude but opposite in direction on the wing. This follows the principle outlined in Newton's third law, the concept of action and reaction. The top surface of an airfoil generates lift by exerting a downward force on the air as it flows past. According to Newton's third law of motion, the molecules of air passing over the wing must exert an equal and an opposite force, in this case an upward force, on the airfoil. We must also consider the impact of the bottom surface of the wing. The airflow along the bottom of the wing is also changed, which results in a force being exerted on the wing, but in this case in a downward direction. For our asymmetrical wing, where the top curve is sharper than that on the bottom of the wing, the force pulling the wing up is larger than the force pulling the wing down, and we still have positive or upward lift. For an under-cambered or convex concave wing, such as those found on the first gliders and early aircraft, the bottom surface acts differently. As the bottom surface is concaved or curved inward, the air is pushed downward by the shape of the wing. If the air is pushed downward, it would push the wing upward. Now both the top and bottom surfaces are being pushed in the same direction, both generating positive lift. Newton still does not explain lift generated in our paper airplane wing, whose top and bottom surfaces are exactly the same length and shape. Nor does it address aircraft that have symmetric airfoils, or modern low-drag airfoils on which the bottom surface is actually longer than the top. Neither theory explains how airplanes can fly upside down. If neither the supporters of Bernoulli or the supporters of Newton's concepts could explain the generation of lift in all circumstances, there must be another piece of the puzzle missing. As a wing moves through the air, the wing is tilted to the flight direction at some angle. This is partially due to the impact of gravity pulling the aircraft downward. The angle between the chord line in the wing and the flight direction is called the angle of attack. This angle of attack has a large effect on the lift generated by a wing. When an airplane takes off, the pilot applies as much thrust as possible to make the airplane roll along a runway. But just before lifting off, the pilot rotates the aircraft. The nose of the aircraft rises, increasing the angle of attack and producing the increased lift needed for takeoff. The wings of an aircraft are typically placed on the body of an aircraft at a small upward angle. This angle of attack changes how the air impacts the wing, particularly the bottom curve of the wing. If the airfoil had been symmetric, the lift would be zero at a zero angle of attack, as the upward and downward forces would be the same. By increasing the angle of attack, the curve on the top side of the wing becomes larger. The molecules have to curve farther, generating a larger upward force. The bottom of the wing now has to push the molecules going under the wing in a downward direction to get them past the back of the wing. This downward push results in an upward force on the wing. This upward force counteracts some of the downward force produced by the curve of the bottom of the wing. This angle of attack would also help to explain the flight of a paper airplane or an aircraft flying upside down. The paper airplane is falling through the air, so the wind is hitting the wing at an angle of attack greater than zero. There is a change in motion of the wind at the front or leading edge of the wing, which should support both Newton's action-reaction concept and Bernoulli's velocity-pressure theory. Past the initial turn, the distance the wind must travel is the same both over and under the wing, so Bernoulli's concept would not apply. The angle of attack forces the wind under the wing at downward, causing an upward force to be applied to the wing. To fly an aircraft upside down would require the pilot to fly with the nose pointed upward or downward from the pilot's perspective to provide an angle of attack to the airflow and enough lift to keep the aircraft airborne. The size and shape of the wing, the angle at which it meets the oncoming air, the speed at which it moves through the air, even the altitude which an aircraft flies, the air density, and air temperature all affect the amount of lift a wing creates. This explains why airplanes have a flight ceiling, an altitude above which it cannot fly. As an airplane ascends, a point is eventually reached where there just isn't enough air mass to generate enough lift to overcome the airplane's weight. It should be noted, however, that neither Daniel Bernoulli or Isaac Newton ever attempted to explain aerodynamic lift generated by flying machines that were developed long after they lived. The lift generated by the wings, and to some extent the body of an aircraft, enable it to fly. To fly, however, the lifting force must exceed the force of weight. In the other lessons in this section, we will be discussing weight, drag, and thrust. All three are impacted by the lifting force of the aircraft.